question remains a circular footing is to be designed to carry a concentric column load of 1000 kilonewton. The footing will be placed at a depth of 1.3 meter in a partially saturated soil, which has a unit weight of gamma of 20 kilonewton per cubic meter and a shear strength parameter of 18 kilonewton per square meter. And these are the parameters, and we have the internal angle of friction to be 20 degrees. Now the question is, assuming that the weight of the foundation is ignored and two, the excavated soil will not be backfilled, determine the minimum diameter of this circular footing. All right, so we're going to work on this and let's see how we can obtain the diameter, the minimum diameter of the footing. We are not going to talk about the thickness of the footing. Uh, in obtaining thickness of footing, we make use of code requirement. So you need to make use of your code using the punching shear requirements to obtain the thickness of your footing. So we are not going to obtain the thickness. We just want to obtain the diameter of this particular circular footing. Now, in the case of a square footing, we do the same. All we just need to do is to get the dimension of the footing, the square side. If the rectangular footing, the same thing. Also, thickness of any footing, it is code. It must be code checked. Okay, using the punching shear requirement for your respective code. All right. So now let's go over and let's work on this particular one. In that question, we are going to solve the problem using Terzarghi's ultimate bearing capacity formula. Now, from Terzarghi's ultimate bearing capacity formula, we have the QU, which is the ultimate bearing capacity, to be 0.5 gamma B N gamma subscript plus NC and C plus Q naught NQ. And these are the ultimate bearing capacity formula by Terzarghi. Now, the internal angle of friction of this soil is 20 degrees. So if we calculate the value of our NC, we'll have our NC to be 17.69. So we'll have 17.69, our NQ to be 7.43, and our N gamma to be 5.0. So now the next thing we want to look at are the shape factors. Remember, we are dealing with a circular shape, so we are going to have the shape factor as our S gamma. Like I told you before, for circular footing, we have a shape factor of 0.6. Our shape factor due to overburden, we have it to be 1.0. That one is constant, always 1.0. Now we have our SQ, which is a shape factor due to shear strength of the soil, and we have it to be 1.3 for a circular footing. Now the next thing we want to do is to apply these coefficients into our ultimate bearing capacity formula, which I'm going to do. Applying the coefficients into the ultimate bearing capacity formula, we're going to have the general formula as this. All right. Now, the net effective overbody pressure, like you see from here, the effective overbody pressure is gotten by minusing the overbody pressure due to Terzarghi minus the unit weight of the soil. So we have the general formula to be 0.3 gamma BNY plus 1.3 NCC plus Q naught. We'll have NQ minus N1. Then we'll have the overburden pressure NQ to be gamma DF, where gamma represents the unit weight of the soil. We'll have DF to represent the effective excavated, the depth of the foundation. All right, so we have the ultimate bearing capacity. Substituting the values into this expression of ultimate bearing capacity, we're going to have the expression to eventually to become our 30B plus 50, 581.126 kilonewton per meter square. So this gives us the ultimate bearing capacity by Terzarghi for this particular circular footing. Now the next thing we are going to check is the safe bearing capacity. The safe bearing capacity, we call it our Q safe. Now solving for our Q safe, we are going to have it to be divided by factor of safety of 3.0. So Q safe for a factor of safety of 3.0. We'll work this one out. We are going to have it to be 10B plus 193 plus 193.708 kilonewton per meter square. This represents the soil pressure and the soil bearing capacity for this particular problem. Now let's look at other things we are going to consider. Now in the question we are told that the soil is excavated and the excavated soil is not used as a backfill. Now, if the excavated soil is not used as its backfill, what it means is that we'll have the foundation as this. We're going to have of heaps of soil around the excavated foundation. This heap of soil, they are going to act as a kind of surcharge load on the foundation. So if that is going to be, it means the total bearing capacity of the soil, but this case is not going to be factored. It's not going to be factored by factor of safety. So we are going to add it up to this pressure due to Terzarghi. So if we add it up, we are going to have this excavated soil, which has a depth equal to the depth of the foundation, and we know the unit weight of the soil. So all we need to do is to bring it together, multiply the unit weight of the soil times the depth of the excavated soil. That gives us the surcharge pressure. I say additional surcharge pressure. So if we add it up, we're going to have this expression to become this. So the Q safe, which is the safe bearing capacity of the soil, becomes 10B plus 219 becomes 10B plus 219.78 kilonewton per meter square. So this gives us the safe bearing capacity of this soil. Now the next stage is looking at the loads acting on this soil. We know that the load acting on the soil is going to be gravity load. So we have gravity load that are acting on the soil. Under the influence of gravity, we have the total load acting on the soil, which is service load, and that service load is 1,000 kilonewton, according to our question. So we are going to work on that. Let's check for that stress that is produced due to this gravity load of 1,000 kilonewton. At the gravity load divided by the cross-sectional, the circular surface of this circle. So, and the area of that circular surface is pi d square, where d represents our diameter. In this case, our d becomes b, so it becomes pi b square over 4. So when we solve for the stress, we'll have this thing to become 127.275 b square kilonewton per meter square. So this represents the stress at the level of the foundation, 1,000 kilonewton, which is also a service load. The stress produced by this load acting on a circular cross-section of the footing is going to be 1,000 divided by the cross-sectional, the circular surface of this circle. So, and the area of that circular surface is pi d square, where d represents our diameter. In this case, our d becomes b, so it becomes pi b square over 4. So when we solve for the stress, we'll have this thing to become 127.275 B square kilonewton per meter square. So this represents the stress at the level of the foundation. Now, having known the stress induced due to this gravity load, we're going to check whether the soil pressure will be able to sustain this stress that is coming on it. Now, for stability's sake, we know that the stress due to gravity load should be less or equal to the stress produced by the foundation. That is the upward pressure from the foundation, the resisting pressure from the foundation. So if the resisting pressure from the foundation, which represents our bearing capacity, it must be greater than the applied stress. So we are saying that the stress due to gravity load should be lesser or equal to our stress, our allowable stress resistance, which represents our bearing capacity. So if we solve for that, we need to obtain what the allowable diameter of this footing will be based on that. So what we are saying, if we simplify it further, we'll have this expression to become this. Now the function f of b for what we have done is that the function f of b should be greater than 127. So all we need to do is to make some trial and error to find out what is the minimum size of the footing that will satisfy the requirement for stability. what minimum size of the footing will satisfy the uh, the requirement for stability. So let's start with 2 meters diameter footing. We'll start with a 2 meter diameter footing. We can say that when we solve it, substitute it into this expression. Or let's start, if you start with 1, you can start with 2, you can start with whatever. But if you start with 1, of course, you know that if you put 1 here, here becomes 1, you put 1 here becomes 1. So we're having about 23, which is not greater than 127.27. So the next we'll do is to try 2. When we try 2, we're going to have B to be 95, which is still adequate. We're going to try 2.5. If we try 2.5, we'll have our function to be greater than 127, which is okay. So since it's okay, we can see we can choose a diameter of 2.5. But we can see from the board that 152.93 is highly higher than 127. So we can reduce it if you want to be economical. You can say when B is equal to 2.3, when B is equal to 2.3, you are going to have 128.3, which is closer to 127, which is conservative enough. So I can decide to settle for this. You can settle for this or this, whichever you choose. But for economic purpose, I need to come down. I will say choose a circular diameter of, let's just settle for an intermediate point between both. I'll say let's choose 2.4. So I've chosen 2.4 meter as the diameter of my footing. So this is how you size a footing um, for your foundation. Now the next we are going to look at is a square footing. How do we size a square footing? In this second example, we are going to look at a case whereby the excavated soil is used as a backfill. So of course, the difference is not much. The only difference is that we are not going to see a surcharge load again. We're just going to apply the formula straightforward. Thank you very much for watching. If you are new, if you are new to this channel, please do wait to hit the subscribe button. I'll see you in our next video. Take care.